Okay, so this is an example of solving a trigonometric equation in an interval. I didn't write it on here, but let's say in the interval, let's say 0 to 2 pi, just to make things a little bit more manageable for ourselves. Now, the way this is set up, 1 plus cosine theta equals 2 sine squared theta, we have a sine squared. Now, what we need is to have only cosine and no sines, or alternatively, only sines and no cosines, but it's going to be easier to go with cosines only because cosine theta is cosine theta. Now, when you have a square on your trig function, that means you can use one of the Pythagorean identities. So what we're going to need to do is, get that out of the way, we're going to need to use, let me change the color here. We're going to need to use the Pythagorean identity cosine squared theta equals, oops, not equals, plus. Cosine squared theta plus sine squared theta equals 1. Now if I subtract cosine squared theta on both sides from this equation, I get that sine squared theta is equal to 1 minus cosine squared theta. And that's what I want to replace the sine squared theta with. So now I'm going to have 1 plus cosine theta equals 2 times 1 minus cosine squared theta. Which, it might seem like that didn't help, but you'll see that this is an essential step. We really can't do anything else besides this. We could shuffle, we could move the 1 over, we could divide by 2. Those things aren't going to really get us any traction until we get rid of that sine, turn it into a cosine. So now we can actually really get started. So there's a couple of ways to proceed here, and I think what's going to be easiest to make what's happening most clear is to do what's called a substitution, where that cosine is really kind of in the way. So I'm going to say that u, and I could use any letter, v, k, p, whatever. I'm picking u, equals cosine theta. And again, this might seem really cryptic or myopic. Like, what is this? But you'll see. So I'm going to make this replacement. This cosine theta will, of course, become u. And this cosine squared theta, that will become u squared. So this equals 1 plus u equals, that's not a very good u, looks like a 4. Let's fix that. 1 plus u equals 2 times 1 minus u squared. And this might be starting to look more manageable and recognizable. I'm going to distribute the 2. So I'm going to have 1 plus u. Oh, I was rubbing my nose there just a little bit. Hopefully that does not make a bunch of extra noise. 1 plus u equals 2 minus 2u squared. And you might go, oh, this is a quadratic equation. And that's exactly how we're going to solve this. So I need to subtract 1 from both sides and subtract u from both sides to get everything onto the right-hand side. Or the left, it doesn't matter, but I'll go with the right-hand side. So then I'll have 0 equals, well, if I subtract 1 on both sides, I'll have 1 minus 2u squared and then minus u. So this is not in descending order. This is not the general form for a quadratic. So I'm going to go ahead and do that and just rearrange it a little bit. So I get 0 equals negative 2u squared minus u plus 1. And this one's set up, when I wrote the problem, to factor in a relatively easy way. That's not necessary. If the original equation were a little bit more complicated, maybe that 2 was like a 7 or something, or whatever, what have you, then it would not be so straightforward. But this one factors, so we'll go with that. So this one factors as 0 equals, I'm going to divide by -1 first, because I don't like that -1, that negative coefficient. So I'll divide by -1 first. So 0 equals 2u squared plus u minus 1. Now this factors 0 equals, parentheses, 2u minus 1 times u plus 1. And when in doubt, when you're factoring, I like to do this. Multiply those two guys, I get negative u. Multiply those two guys, I get 2u. Do those two add up to make the middle term? Oh, they do. Negative u plus 2u makes 1u, which is what I have right here, right? 1u. Okay, so let me get rid of that. That's just a check that I can make for myself. If I'm confident that I'm doing it right, maybe I don't need to do that. And now, another alternative is just use the quadratic formula. If you want to, you can use that. Anyway, now I can separate these two factors. So 0 equals 2u minus 1. And at this point, looking at what we've got so far, you might even not notice, you might not recall, or someone looking at the middle of this might not even know this is a trig problem. Remember, u is cosine theta the whole time. I'm just writing it this way to make it visually easier to deal with. Also, 0 equals 2u minus 1, or 0 equals u plus 1. I'm going to focus on this equation first. I'm going to add 1 to both sides. So 1 equals 2u. Then I'll divide by 2 on both sides. 1 over 2 equals u. But I'm not going to write u, because now, for at least for this branch of the problem, the algebra part is kind of done. I'm going to put the cosine theta back in, right? That guy there. So 1/2 equals cosine theta. Okay, and now I can ask, okay, well, what angle values, when substitute in for theta, would cause cosine to be 1/2? So I can think about the unit circle, and I guess I'll draw a unit circle over here. Oops. You know what? I should be using these auto features more. There we go. That's close enough, right? So if cosine is 1/2, that's like right about here. This is a unit circle. That's about at the 1/2 point. So I want these two positions, right? And if you think about your unit circle, oh, well, that's pi over 3 and negative pi over 3, right? So let's write that down. Theta equals pi over 3 and negative pi over 3. Right? But there is a slight problem with that. And you might have thought of it right away. This is not quite right. And maybe you don't see why. So let's go back up here. Remember I said we're going to solve in this interval, 0 to 2 pi. So there are no negative values. And again, if you think about it, cosine's periodic. There's really infinitely many theta values that cause cosine to be 1/2. But we just want the ones in the interval. So how do I get that? Either I can have that in mind from the beginning, when I'm thinking about the unit circle, I can have in mind, oh, I need to make sure I'm in the right interval. Or I can modify this one. I can add the period of cosine. I can add 2 pi to it. Say, oh, well, really, I meant to have plus 2 pi with that guy the whole time. Oops. Over 3. No, I'm sorry. What am I doing? Oops. 2 pi. Just 2 pi, not a fraction. But really, if I wanted 6 pi over 3, right? So this is the same as having pi over 3 and 5 pi over 3. Okay, so that's that branch of the problem done. Now I can go focus on this guy. I can subtract 1 from both sides. So I get negative 1 equals u. And I can, well, you know what? Equals cosine theta, right? Negative 1 equals cosine theta. So then I can ask, okay, what angle values, so then substitute for theta, would cause cosine to be negative 1? Well, that's over here on the left edge of the circle, right? When x equals negative 1. Well, what angle is that? Well, that's going to be pi radians. So theta equals pi. So my final solution list of all the solutions is theta equals pi over 3, pi, and 5 pi over 3. That 5 is a little janky, but good enough, I guess. So there we go. There's my solution. That's done. So if we were to go take any of these three numbers and plug them back into the original equation, right, it would solve that. And you can check that. Oops, let's not go too far. And you can check that on your own. Just plug it in. You'll see that you get the same thing either way. Yeah, so that's the overall procedure. Since this one is quadratic in form, which you can tell, right away, sine squared, that means it's quadratic in form. This is the overall procedure. Do replacement, use a Pythagorean identity, and then basically you're solving an algebra problem, something you've done probably dozens of times, and then you turn it back into a trig problem at the end.